The topic of today's lecture is inverse transformations and inverse matrices. But we begin with the definition of an inverse function. In mathematics, it is often desirable to be able to undo a function that we apply. So, as an example, let's consider a function f of x is equal to x cubed, where x is a real number. So here, the inverse operation for this, that we will denote f inverse of x, is the cube root of x. So the cube root of x operation will undo the x cube, and vice versa. The x cube operation will undo cube root of x. So let's give a definition. So let f be a function from a set A to the set B. So be a function between sets A and B. A function g from B to A is called the inverse of f if the compositions, so g composed with f, so this becomes a function, well, from A to B and then from B to A. So this is a function from A to A. And we require that this is identity transformation on the set A, and the composition f with g, so and f composition with g is identity transformation. Well, this one will act from B to B through the set A, is identity on the set B. Now, what's an identity transformation? So identity, say, on a set A is a transformation from A to A with the property that identity of any element is the element itself. So it's a transformation that does effectively nothing. Now, here we can see that indeed, according to this definition, these two functions are inverses to each other. Right, so this is f of x and this is our g of x. So now let us see what is the composition g with f. So this is g of f of x. So this is g of x cubed. And so this is cube root of x cubed. And we know that the cube root of x cubed is equal to x for all real numbers x. So this tells us that g composed with f is identity. And the f of g of x, so this is f of cube root of x. So this is cube root of x all cubed, and again we know that the result is x, so this tells us that f composed with g is also identity transformation. So according to this definition, so these two functions are inverses of each other. Now diagrammatically, so if we have a function between sets A and B, so the function f goes in this way, then the inverse function will just reverse all the arrows. So it will go like this. So this will be the function g. And so that we have these two compositions. So if we go back and forth, then we come to the same place. Or, so if we start from the set B and first follow the g arrow and then come back with an f arrow, again we will come to the same point. So this is how one should picture the function and its inverse. not every function has an inverse. And next, so let us investigate the question. So when a function has an inverse. Definition. A function f from a to b is called bijective if f is injective and surjective. So these two properties together, so injectivity and surjectivity together, is called bijectivity. Now, so let's recall, what does it mean that f is surjective? So this means that for every b in the set B, there exists an element A in the set A such that B is f of A. So in other words, so every B in the set B has a pre-image in A. So this says that A is a pre-image of B because A is mapped to B by function f. And f is injective. So this means that for all A1 and A2 in the set A, if f of A1 is equal to f of A2, then this implies that A1 is equal to A2. Now, this can be expressed in the following way, that every B in B has at most one pre-image. So meaning 1 or 0. And indeed, so why can't B have two pre-images? So suppose an element B here has two pre-images. So this equality says that A1 is a pre-image of B and A2 is a pre-image of B. So injectivity says that this implies that A1 is equal to A2. So this means that this definition of injectivity precludes B from having two distinct pre-images. So it is possible that B has no pre-images at all. So that does not contradict injectivity. But so this says that the number of pre-images is either 0 or 1. So now, combining these two properties together, we get that f is bijective. So this is equivalent that every B in B has a unique pre-image in A, right? So like by surjectivity, a pre-image exists, and by injectivity, we cannot have more than one pre-image. So this means that every element B in the set B has exactly one pre-image. So this could be written with quantifiers in the following way. For every B in B, there exists an unique, so this exclamation mark means unique, A in the set A, such that B is equal to f of A. Let us state a proposition. Let f from A to B be bijective. Then f has an inverse function G from B to A. Now let's give a proof of this. So we need to define the value G of B for any element B in the set B. But we know that F is bijective. So F is bijective. So this implies that there exists a unique A in A such that B is equal to F of A. And then we use this property to say that we set G of B to be equal to A. Right? So if we have an element B in the set B, right? So we find its unique preimage A in the set A, and we say that G of B is equal to that element A. So what we get here is that B being equal to F of A becomes equivalent to saying that G of B is equal to A. So now, what do we need to show? So we need to show that the composition of G with F is identity on the set A, and the composition of F with G is identity on the set B. Now, let's consider what is G of F of A. Right? So here, so we know that if F of A is equal to B, then G of B by definition is equal to A. And so this tells us that here F of A, we call it B, and we get G of B, and that's A. And so this tells us that the composition of G with F is equal to identity on the set A. So similarly, if we consider F of G of B, right? So then we know that if G of B is equal to A, so this means that A was a preimage of B under F, by definition of F. So this says that F of A is equal to B. And so here we have F of A, and this is B. And so again, we see that F composition with G is identity on the set B. So now we prove this proposition that every bijective function is invertible. And in fact, the converse of this is also true. And every invertible function is bijective. So this is what we're going to prove next. Proposition: let F from A to B be invertible with an inverse function G from B to A. Then F is bijective. So for the proof of this, we need to show that F is surjective. So this means that for every B in B, there exists A in A, such that B is equal to F of A. And also that F is injective. And this property is that for all A1 and A2 in A, f of A1 being equal to f of A2 implies that A1 is equal to A2. Now, let's start. So, okay, let's call this 1, surjectivity, and 2, that it's injective. So let's start with 1. So here we need to prove something that starts with a universal quantifier. So our method is, we say, let B be an arbitrary element of the set B. So let B be an arbitrary element in the set B. So what we need to show is that there exists an A such that B is equal to f of A. So how do we construct this A? A is the pre-image of B. But this pre-image now may be obtained by applying the inverse function to B, right? So, and we said that we have an inverse function. So then we take A to be G of B. So we claim that A is a pre-image of B under F, right? So this is what we need to show. So for this, we need to calculate what is f of A. Well, f of A is f, and A was G of B. So we have f of G of B. But by definition of inverse functions, composition of f with G is identity on the set B, applied to B. And so we get that the result is B. And what we proved is that B is equal to f of A. And so this means that B has a pre-image of B. Well, B has a pre-image under F, right? And so this is now holds, and this means that F is surjective. Now, let us prove 2. So here, again, we have a universal quantifier. So we say that for all A1 and A2, something holds. And again, we say, so let A1 and A2 be arbitrary elements of A. Now, we need to prove an implication that X implies Y. So to prove this, we say, let's assume X, and let's derive Y from that. So we assume that f of A1 is equal to f of A2. Right? So now we need to prove, so we need to show that A1 is equal to A2. Now, how do we prove this? So if f of A1 is the same as f of A2, then let's apply G to both sides. So this will imply that G of f of A1 is equal to G of f of A2. But, so what's the composition of G with f? Well, by definition of inverse function, this is identity on A. And so this means that the left-hand side here is just A1, and the right-hand side is just A2. And this gives us exactly what we need. And so this proves that if f of A1 is equal to f of A2, then A1 is equal to A2. And this is the injectivity property. So we proved that if f has an inverse, then f is bijective. And so now we combine these two propositions, and we obtain that a function is invertible if and only if it's bijective. Or bijective means also that we have a one-to-one correspondence between elements of the set A and elements of the set B, right? So these arrows from A to B are surjective and injective. So this means that every element in B has a unique preimage in A. Now, let us look at inverses in the context of linear transformations. So let T from V to W be a linear transformation. So then T has an inverse S from W to V if and only if T is bijective. So what are equivalent ways of saying this? Well, bijective means surjective and injective. So surjective means that image of T is the whole space W, and injective for linear transformation is equivalent to saying that the kernel of T is the zero vector. Or yet another way is remember that bijective linear transformations we called isomorphisms. So T is an isomorphism. By definition of an inverse transformation, so we have that S composed with T is identity transformation on the space V, and T composed with S is identity transformation on the space W. If T is a linear transformation which is bijective, then from the general theory of invertible functions, we know that T has an inverse function, S. But we also would like to establish the fact that S is in fact a linear transformation. So, proposition. So if T from V to W is a linear transformation, and S is the inverse of T, right? So in this sense, then S from W to V is also linear. So the proof is going to be based on the property of inverse functions that we see. That if W is T of V, right, so then this is equivalent to saying that S of W is equal to V, right? So these two statements are equivalent to each other for inverse functions. Okay, so let's give a proof of this proposition. So what do we need to show? So we need to show that for all W1 and W2 in W, S of W1 plus W2 is equal to S of W1 plus S of W2. Right, so this is property 1. And property 2 is that for all W in W and for all C in the field, S of C times W is equal to C times S of W. So this is what we need to prove. Now, let us look at 1. So suppose, so let's call S of W1, let's call V1, and S of W2, let's call V2. So then T of V1 plus V2 is equal to T of V1 plus T of V2, because T is a linear transformation. And so saying that S of W1 is V1, so by this principle says that T of V1 is W1. So this is equal to W1 plus W2. And then we apply this principle again. So here we have that T of V1 plus V2 is something. So this means that if we apply S to the right-hand side, then we are going to get V1 plus V2. So this tells us that S of W1 plus W2 is equal to V1 plus V2, right? So if T sends this vector to W1 plus W2, then S sends W1 plus W2 to V1 plus V2. Well, V1 is, by our definition, S of W1, and V2 is S of W2. And now we prove that S of W1 plus W2 is equal to S of W1 plus S of W2. And that's exactly our first property. Let T be a linear transformation from Fn to Fm with M by N matrix A. So what we would like to understand is how invertibility of T is connected with the properties of matrix A. So we know that T is invertible if and only if T is bijective. So which means that T is surjective and injective. Surjectivity of T is equivalent to saying that the image of T is the whole space Fm, while injectivity of T is equivalent to saying that the kernel of T is the zero vector. So now let us relate this to matrix A. So what is the image of the transformation, and how is it related to matrix A? And so we know that the image of a transformation corresponds to the column space of the matrix. So we get that column space of A is Fm. Now, and how is the kernel related to matrix A? So the kernel is the null space. So null space of A is the zero vector. Okay, so now we expressed surjectivity and injectivity of T in terms of the column space and the null space of a matrix. Now, when is the column space of a matrix is the full space Fm? So that can be expressed in terms of systems of linear equations. So we can say that this happens when Ax is equal to B is consistent for all right-hand side columns B in Fm. Right? So because any vector in the image of the transformation can be interpreted as A times something. Right? And so here, if we say that the image of T is Fm, so this means that any vector B in Fm can be expressed as A times some vector from Fn. And so the fact that the null space of a matrix is 0 also can be expressed in terms of systems of linear equations. So this will say that the system AX is equal to 0 only has a trivial solution X is equal to 0. We looped back to the very beginning of our course, and now we're already talking about systems of linear equations. So we connected properties of linear transformations to properties of systems of linear equations. And we solve systems of linear equations by bringing the matrix to row echelon form. The system AX equals B is consistent for all possible right-hand sides if and only if row echelon form of A has no zero rows. While saying that the system AX is equal to 0 only has a trivial solution X equals 0. So this means that the system AX is equal to 0 has no free variables. Because if we do have free variables, we can assign them any value, including non-zero values, and then we will get non-zero solutions. So now, what is this in terms of pivots? Every non-zero row of row echelon form of a matrix starts with a pivot. So if we have no zero rows, so this means that row echelon form of A has a pivot in every row. And so let us recall which variables are free and which are leading. So leading variables correspond to pivot positions. And free variables correspond to columns that have no pivots. So if we have no free variables, so this means that row echelon form of A has a pivot in every column. And we get our conclusion. So that a linear transformation T with matrix A is invertible if and only if row echelon form of A has a pivot in every row and in every column. So we get the following conclusion, that T is invertible if and only if number of pivots of row echelon form of A is equal to the number of rows of A and is equal to the number of columns of A. In particular, we conclude that the number of rows and the number of columns must be the same. So we get the following necessary condition for invertibility of T. If T is invertible, then n must be equal to m, right? So because m and n determine the size of our matrix. Of course, this equality of m and n is only a necessary but not a sufficient condition for invertibility. Because if we just know that the number of rows and the number of columns are the same, this doesn't mean that the number of pivots of row echelon form are also equal to this number. So we could have equal dimensions, but fewer pivots, and then such a transformation will not be invertible. But if these two dimensions do not match, then we immediately can conclude that this transformation cannot be invertible. So we can also state this as the following theorem. So let T be a linear transformation from V to W, where V and W finite dimensional. If T is invertible, then dimension of V must be equal to dimension of W. So here, when we have finite dimensional vector spaces, we can choose bases in V and in W. And so if dimension of V is n and dimension of W is m, then V is isomorphic to Fn and W is isomorphic to Fm. And then once we fix these bases, we can construct the matrix of this transformation. And so then exactly this the same argument applies to this matrix, and so we obtain this theorem. Now let us look at the situation when we do have a chance for invertibility. So let T be a linear transformation from Fn to Fn with a square n by n matrix A. So what can we say about reduced row echelon form of the matrix in this case? Right? So if T is invertible, right? If and only if, so the number of pivots in reduced row echelon form of the square matrix A is equal to n. But how can a reduced row echelon form look like if we have an n by n matrix and we have n pivots? So the only possibility for this reduced row echelon form is this one, right? So this is the only reduced row echelon form of an n by n matrix with n pivots. So we have ones on the diagonal, so these are our pivots, and zeros elsewhere. So we say that in this situation, T is invertible only if and only if reduced row echelon form of A is, so this we call identity matrix. So is identity matrix, right? Identity. So this is the matrix of identity transformation. Now, we can also say the following, that, well, for square matrices, automatically we know that the number of rows is equal to the number of columns. So if we know that the number of pivots is equal to the number of rows, then automatically the transformation is invertible, because then it's also equal to the number of columns. But equality of the number of pivots to the number of rows is equivalent to the fact that T is surjective, because surjectivity is the equality of number of pivots to the number of rows. And injectivity is the equality of number of pivots to the number of columns. So what we see is for n by n transformations, right? So for transformations from n-dimensional space to n-dimensional space, invertibility is equivalent to just one of the two properties, that T is surjective or T is injective. So in general, for invertibility, we need to require both properties. But if we know that these two dimensions are the same, then one property will force the other, because equality of number of pivots to the number of columns will imply equality of the number of pivots to the number of rows, and vice versa. Now, suppose a transformation T from Fn to Fn with matrix A is invertible. And let S be the inverse of T and has matrix B. Now, what can we say the connection between matrices A and B? So we know that by definition of the inverse, if S is the inverse of T, so this means that T composed with S is identity transformation, and S composed with T is identity transformation. Now, let us write down matrices of these transformations. So we know that a composition of transformation corresponds to the product of matrices. So more precisely, the matrix of the composition is the product of matrices of each transformation. So this means that the matrix of the left-hand side is going to be A times B. And the matrix of the right-hand side, so the identity transformation, has this identity matrix. And the same holds in the opposite order. So B times A is also identity matrix. So what we see is that the fact that a pair of transformations S and T are inverses of each other, so this is equivalent to saying that A times B is identity and B times A is identity. So this motivates the following definition of an inverse matrix. So we have the following definition. Matrix B is called the inverse of matrix A. So notation B is equal to A inverse. If A times B is equal to identity and B times A is also equal to identity matrix. So from what we saw before, that only square matrices could be invertible. So this means that non-square matrices never have an inverse. And square matrices, some of them would have an inverse and some wouldn't. So this depends on the reduced row echelon form of a matrix. Let us now look at some examples. So let us consider the following transformation. So rotation, transformation. So let's call it R alpha, which is a rotation of a plane. So this is rotation transformation. So by angle alpha counterclockwise. So if we rotate the plane by angle alpha counterclockwise, how can we undo this transformation? So that is find the inverse. To undo this transformation, clearly we need to rotate the plane by angle alpha clockwise. Or, so this is the same as saying that, so rotate the plane by angle minus alpha. So this means that R alpha inverse is equal to R minus alpha. Let us look at the matrices of these transformations. So the rotation matrix is the following. So it's cos alpha, sine alpha, minus sine alpha, cos alpha. So what is the matrix R minus alpha? So this is the matrix cos of minus alpha, sine of minus alpha, minus sine of minus alpha, and cos of minus alpha. But the cos function is even. So this means that cos of minus alpha is the same as cos alpha. And the sine function is odd. So sine of minus alpha is minus sine alpha. And so here we get plus sine alpha. And here we get cos alpha. Now, our prediction is that because these are two transformations that are inverses to each other, our prediction is that the product of these two matrices is the identity matrix. So let us check this. So we have cos alpha times sine alpha minus sine alpha cos alpha times the second matrix is cos alpha minus sine alpha times cos alpha. Now, when we multiply matrices, we take dot products of rows with columns. So here we get, in the first entry, we get cos squared alpha plus sine squared alpha. So when we take the dot product of the second row with the first column, we get sine alpha times cos alpha minus cos alpha times sine alpha. That cancels, and we get 0. So if we take the dot product of the first row with the second column, we get cos alpha times sine alpha minus sine alpha times cos alpha. That's 0 again. And when we take the dot product of the second row with the second column, we get sine squared alpha plus cos squared alpha. And from trigonometry, we know that sine squared plus cos squared is equal to 1. So what we get is we get a 2 by 2 identity matrix, as we have expected, because these two transformations are inverses of each other. For our next example, so let us take a transformation T from R2 to R2, which is a reflection with respect to line y is equal to x. Now, so how does this transformation works? So if we have some vector v, then to transform it, so we treat the line y equals x as a mirror, and we find the mirror image of this vector with respect to this line. So this will be t of v here. So now, so what is the inverse of the mirror reflection transformation? So how do we undo mirror reflection? Well, it's clear that to undo mirror reflection, we need to apply it again. So what we have, that the inverse of this transformation is itself. So if we apply mirror reflection twice, then we get identity transformation. So now let us confirm this with matrices. So how can we write down the matrix of a mirror reflection transformation? So here we use our mantra. So to construct the matrix of a transformation, take the images of basis vectors and place them as columns. So the first basis vector, so 1, 0. So if we reflect it, so we need to find its image. So we need to reflect it with respect to this mirror, and we see that the mirror image of the vector 1, 0 is the vector 0, 1. So this tells us that the first column of this matrix is 0, 1. So the image of the first basis vector under this transformation. Now, the second column is the image of the second basis vector, but by symmetry, so 0, 1 will be transformed into 1, 0. So this tells us that the second column of this matrix is 1, 0. So then, this equality that T inverse is equal to T, so this tells us that if we multiply T by itself, we get identity transformation, right? So this is another way of saying that T inverse is equal to T. So with matrices, so we need to calculate A times A, which will also denote A squared. And so this product of A with itself must be the identity matrix. So let's check this. So matrix A is 0, 1, 1, 0. And we take it twice. And now we multiply. So when we take dot products of the first row with the first column, we get 1. If we take the dot product of the first row with the second column, we get 0 times 1 plus 1 times 0. That's 0. So the dot product of the second row with the first column is 1 times 0 plus 0 times 1. That's 0. And the product of the second row with the second column is equal to 1. And indeed, so we see that, as expected, we get the identity matrix here. Now, let us discuss the relation between compositions of transformations and inverses. So we have the following theorem. So let T be an invertible linear transformation from the space U to the space V. And let S be an invertible linear transformation from the space V to the space W. Then, so we can take a composition of these two. So first we can apply T, and then we apply the S. So here we get the composition of S with T, and we claim that this is invertible. And so we want to express the inverse of the composition in terms of the inverses of S and T. Now, let us try to guess what is the formula in the right-hand side. Now, let us consider the diagram here. So T sends U to V, and S sends V to W. And so we can come back, so with S inverse, so we can undo S going from W to V, and we can undo T by going from V to U. Now, so how can we invert the composition? So here the composition goes from U to W. So to undo this composition, we have to first return with S inverse to V, and then return with T inverse to U. So now we have to take the composition of S inverse with T inverse. And when we take the composition, we write the factor that is applied last on the left. And so here, when we come back, the last transformation that we apply is T inverse. So this means that this composition is going to be T inverse with S inverse, right? So first we apply S inverse, it's on the right, and then we apply T inverse, that's a factor on the left. And so what we see here is that curiously, so these factors S and T switch their order in the left-hand side compared to the right-hand side. This phenomenon is sometimes called shoes and socks rule. In the morning, we put on the socks, and then we put on the shoes. When we come back home in the evening, so to undo this transformation, we first remove the shoes and then remove the socks. So don't try to do it in the opposite order. And this natural change of order when we undo our actions is reflected in this formula. We can also express this fact with matrices. So we get corollary. So if A and B are invertible n by n matrices, then their product AB is invertible, and we have the same formula for the inverse of a product. So A times B inverse is equal to B inverse times A inverse. So this is socks and shoes rule. Now let us give the proof of this theorem. So we need to show that T inverse composed with S inverse is the inverse of S composed with T. Now, how do we check that something is an inverse of another transformation? Well, we take compositions in both orders. And if both compositions are equal to identity, then we do have inverses. So we need to compute S composed with T composed with T inverse composed with S inverse. Now, we know that compositions are associative. So this allows us to regroup the brackets in this expression. So this is equal to S composed with T composed with T inverse composed with S inverse. And because T inverse is the inverse of T, the composition of these two is identity. So then we get S composed with identity composed with S inverse. And identity transformation composed with any transformation S gives us S, because identity is a lazy transformation that does nothing. It takes a vector and transforms it into itself. So we get S times S inverse. And because S inverse is the inverse of S, so we get the identity transformation here. And if we take a composition of these two transformations in the opposite order, so if we take T inverse composed with S inverse composed with S composed with T, so clearly the same type of calculation shows that the result is identity. Now we see that if we switch this order, so if we try to use the wrong formula, S inverse composed with T inverse, then this computation simply will not work. Let us discuss one aspect of the definition of an inverse of a transformation. So let T be a linear transformation from V to W, and let S, which is a transformation from W to V, be its inverse. So this means that that the composition of S with T is identity transformation of the space V, and the composition of T with S is identity transformation of the space W. Now, do we really need to require both conditions? Is it enough to ask just for one? So this question motivates the following definition. definition. So again, so let T be from V to W and S be from W to V. Then S is called a left inverse of T if we just take one condition. S composed with T is identity on the space V. And similarly, S is called a right inverse of T if T composed with S is identity transformation of W. Now, let us look at the following example. So let D be a differentiation transformation of the space of polynomials. So dx from Rx to Rx such that D applied to a polynomial f is equal to its derivative. Right? So in particular, D of x to the power n is equal to n times x to the n minus 1. Now, is this transformation invertible? Right? We know that the transformation is invertible if it is surjective and injective. Surjectivity would mean that any polynomial can be written as a derivative of some other polynomial. And this is true. So what we see is that D is surjective. Now, how about injectivity? Injectivity means that the kernel of this transformation consists just of a zero polynomial. Is this true? And the answer is no, because we know that when we apply differentiation to a non-zero constant polynomial, then the result is 0. So this means that D is not injective, because the kernel of D consists of constant polynomials and not just the zero polynomial. From this, we make a conclusion that D is not invertible, because for invertibility, we need both surjectivity and injectivity. Now, let us look at the antiderivative transformation. So now we take let S be a transformation of the space of polynomials R of x to R of x. Well, a linear transformation can be defined on the basis vectors, right? So here we say that S of x to the power n is equal to 1 over n plus 1 x to the n plus 1. So here we take the antiderivative transformation. So what happens if we take the composition of the derivative and antiderivative? So let's take D composed with S applied to x to the power n. So what is this? So this is D of S of x to the power n. Now, S of x to the power n is 1 over n plus 1 x to the n plus 1. And when we take the derivative of this, so we get n plus 1 over n plus 1 x to the power n. So we get x to the power n. So we start with x to the power n, and we recover x to the power n. So this tells us that D composed with S is identity transformation. Now let us look at the composition in the opposite order. S composed with D applied to x to the power n. So this is S applied to the derivative of x to the power n. So this is n x to the n minus 1. And when we take the antiderivative here, so what we get is we get n over n times x to the power n, right? And the result is x to the power n. So now, do we get that S composed with D is identity? Because so then we run into problem, right? So on one hand, so it looks like S is the inverse of the transformation D, but here we said that D is not invertible, right? So what's the contradiction here? Well, the thing is that here we have this n in denominator. So this means that this calculation is valid only if n is not equal to 0, right? And for the space of polynomial, when we take constants, so a constant polynomial is x to the power 0. So for x to the power 0, this calculation is not valid. And so what we should say is, so S composed with D of x to the power n is equal to x to the power n if n is greater or equal to 1. And if we have a constant polynomial, then here we apply differentiation. So when we apply differentiation to 1, we get the 0 polynomial. And S being a linear transformation, it transforms 0 into 0. So what we get is that this composition is 0 if n is equal to 0. So this means that S composed with D is not equal to identity transformation. And our conclusion here, so that D composed with S is identity, but S composed with D is not identity. So this means that S is a right inverse of D, but not a left inverse or a full inverse. And D does not have an inverse because it's not bijective. So let us state the following theorem. So the first part. Suppose T has a left inverse S1 and a right inverse S2. Then S1 is equal to S2 and T is invertible. So the inverse of T is this S1, which is equal to S2. So part 2. So let T be invertible and S1 be a right inverse of T. Then S1 is the full inverse of T. And 3, if T is invertible, then its inverse is unique. So this means that the transformation may have only one inverse. Now let us compare this theorem with this example. So in this example, we see that S is a right inverse of D, and D is not invertible. Then the first part of this theorem actually says that D cannot possibly have the left inverse, because if D had both the right inverse and the left inverse, then they would be equal and they will be the full inverse. But here we know that S is a right inverse, but not the left inverse of D. So if we look at the second part of this theorem, then even if we didn't know that D is not invertible, if we just found the transformation which is a right inverse of something but not a left inverse, then this would immediately tell us that this transformation D is not invertible. Because for invertible transformations, so if we have a right inverse, then automatically this right inverse must be equal to the left inverse. And here, if we check that something is a right inverse but not a left inverse of D, then by second part of this theorem, we conclude that D is not invertible. Let us give a proof of this theorem. So we start with part 1. So suppose we have a left inverse of T S1 and the right inverse of T S2. So consider the following transformation. S1 composed with T composed with S2. So then this product can be calculated in two different ways. So we can use the associative law and say that this is equal to S1 composed with T composed with S2. So here we have that S1 is the left inverse of T. So this means that S1 composed with T is equal to identity. And then we take identity composition with S2, we get S2. Now, by associative law, we can put the brackets on this expression differently. We can write that this is equal to S1 composed with T composed with S2. Right? So this is associative law for compositions. And we know that for compositions of functions or transformations, associative law always holds. And S2 is the right inverse of T. So this tells us that T composed with S2 is identity. And so now we get S1 composition with identity, which is S1. And because these two expressions are equal by associative law, so we conclude that S1 is equal to S2. So now let us look at the second part. So here we are told that T is invertible. And so let's call S to be the inverse of T. Then this inverse of T, S, is both the left and the right inverse. So let us note that, so this tells us that in particular S is a left inverse of T. Well, it's actually a full inverse, so but in particular it's a left inverse. And S1 is a right inverse of T. So then by property 1, right, so if we have a left inverse and a right inverse, they're equal. So we get that S1 is equal to S, so which is T inverse. Right, and this proves part 2. And now for part 3, so let S1 and S2 be two full inverses of T. Then S1 is a left inverse of T. and S2 is a right inverse of T. And again, by property 1, so if we have a left inverse and a right inverse, they're equal. So by 1, S1 is equal to S2. And so this means that there could be only one full inverse of T. And this proves the part 3 of the theorem. I will finish this class with the following problem for you to solve. So, problem. Let A be an invertible matrix. Show that the inverse of the transpose of A is the transpose of the inverse of A. So here we're saying that if A is invertible, then the transpose of A is also invertible. And to compute the inverse of the transpose matrix, we take A inverse and transpose it.